Hello students, I welcome you once again in the digital lecture series of Bajaj College of Science, Wardha. So we have already started the discussion of the sixth unit of Sem 3, that is Ionic Equilibrium and Colligative Properties. This is our lecture 2. In the last lecture, we have studied what are electrolytes, their classification, the concept of degree of dissociation, and the factors affecting degree of dissociation. In today's lecture, we will study another important concept in ionic equilibrium, that is ionization constant. So what is ionization constant? Its definition is very important. The ratio of the product of the activities of the ions produced from a given solute to the activity of the undissociated molecules of that solute. It is called as ionization constant. We have studied that in the ionic equilibrium, on the left hand side, that is reactant side, there are undissociated molecules of the electrolyte, and on the right hand side there are ions which are produced from the dissociation of that particular electrolyte. So now this concept of ionization constant we will study with respect to a weak acid as well as a weak base. Let's first discuss the dissociation or ionization of a weak acid. So consider that there is a weak acid as represented here, HA. Now we know that this weak acid, some molecules, because it is a weak acid, very few molecules will dissociate to produce H plus ions and A minus ions. Now these H plus ions are highly reactive. They will react with water and they will form the hydronium ion. And the A minus ions, that is the anions produced from this weak acid, they will remain inside the solution. So now we know that this reaction will not only proceed in the forward direction, but also there is a considerable amount of backward direction. So the reaction, this is a dynamic equilibrium indicated by the reversible arrow. So the weak acid molecules, they will donate one H plus to the water molecule and it will form hydronium ion, and only anion of the acid will remain inside the solution. So we can apply the equilibrium constant. So the equilibrium constant for this particular dissociation equilibrium, it can be given by this equation. That is Ka is the equilibrium constant of this particular dissociation equilibrium. Ka is equal to the activity of hydronium ion multiplied by activity of A minus ions, that is anions of the acid, divided by activity of undissociated acid molecules and activity of water molecules. Now this particular equilibrium constant of this dissociation equilibrium, which is nothing but the dissociation of weak acid HA, it's called as ionization constant of acid HA. So this is the ionization constant, or you may also call it as the dissociation constant of acid HA. So this is the equation for the dissociation constant of dissociation constant of weak acid HA in terms of activities of the ions and activities of these molecules. But here water is present in large excess. We can consider activity of water to be equal to 1. So putting activity of water into 1 into the earlier equation, we will get this simplified equation, that is Ka is equal to activity of H3O plus ions, that is hydronium ions, and activity of anions divided by activity of Ha, that is undissociated weak acid molecules. Now, this activity represents activity terms. You may be knowing, or if you are not knowing, for your information, remember that activity is the active concentration. And the dilute solution, inside dilute solution, as the molecules or ions are well separated from each other, the activities can be considered to be equal to the concentration. So here the activity of hydronium ion is equal to the concentration of hydronium ions. Activity of A minus ions, that is anions, is equal to the concentration of A minus ions. And activity of undissociated weak acid molecules, that is Ha, it is equal to concentration of Ha. So for dilute solutions, we are replacing all the activity terms by their respective concentration terms. So now this can be considered as the equation of dissociation constant of the weak acid. Now, what will happen if the value of Ka, it is higher? So when the value of this K will be higher? When more number of ions are present. So whenever this numerator is more and denominator is less, K will be high. In which condition the numerator will be high? The numerator will be high when the dissociation is more. So if dissociation is more number of ions are present, less number of molecules are present, hence more is the ionization or dissociation constant, and stronger is the acid. So higher the value of Ka, higher is the acid strength, that means stronger is the acid. So now the next point we have to discuss is the similar discussion that we have done for the weak acid. The same discussion we will do for the weak base. Now the dissociation or ionization of a weak base BOH. Consider that there is a weak base BOH. So this B represents the cation like Na plus or K plus or Ca2 plus, anything. So B is the cation. Here we are considering it as a univalent cation. So BOH is a base. Whenever it will be added to water, what will happen? It will dissociate some molecules. If it is a weak base, only few molecules, they will dissociate to form B plus cations and OH minus cation. Now in the earlier equilibrium as well as this equilibrium, we have shown this AQ. It represents that these ions or the molecules, they are hydrated. That means they are surrounded by a large number of water molecules. Now, the equilibrium constant, this particular equilibrium, dissociation equilibrium, is characterized by the equilibrium constant, which can be given by this particular equation. Because it is the equilibrium constant for dissociation of a base, we are indicating here small b, Kb. So Kb is the ratio of activity of products, multiplication of activity of products. Products are the ions B plus and OH minus. So here we are multiplying activity of B plus with activity of OH minus. And we are dividing this with the activity of base, that is BOH. Now, this Kb, that is the dissociation constant or the equilibrium constant of this dissociation reaction, is called as ionization constant of the base BOH. Or you may also call it as the dissociation constant of the weak base BOH. Again, for dilute solutions, we can replace the activity terms by the concentration terms. Always remember that activity is active concentration, and active concentration may be different from the actual concentration. But for dilute solution, as the ions, they are well separated from each other, the activities are almost equal to the concentrations. So we are replacing activity of B plus by concentration of B plus. We are replacing activity of OH minus by concentration of OH minus, and activity of BOH can be replaced by concentration of BOH. So that is the equation for dissociation constant of the weak base. Now, again, when the Kb will be higher, or dissociation constant of weak base will be higher, if the concentration of ion, sorry, if the concentration of ions is higher, that means if more is the dissociation, more will be the value of Kb, and stronger will be the base. So this Kb is also the measure of the strength of base. Higher the value of Kb, higher is the strength of the base, or stronger is the base. And smaller the value of Kb, weaker will be the base. So when it will be small, when the numerator is less. If numerator is less, when the numerator will be less, then the base will be weak. So less dissociation, less number of ions. And here more number of undissociated molecules in case of a weak base. So the value of Kb will be also very less. Now, the next point that we have to discuss is ionic product of the water. Now, the water can act both as an acid as well as a base. So we call it as amphoteric. So water as a weak acid, it can react with bases to give OH minus ions. And water can also act as a weak base, so it can react with some acids to form hydronium. So water can act as a very weak acid as well as a very weak base. So while reacting with even a very weak base, it is acting as an acid. While reacting with a very weak acid, it is acting as a base. So water can act both as an extremely weak or very weak acid as well as a very weak base. And now whenever we observe water by some special techniques, you will observe that there is some concentration of ions. That is, if you observe the pure water, pure distilled water without any added solute, there is present a small concentration of hydronium ions as well as hydroxide ions. And why this concentration of hydronium or hydroxide ions is present in the even the purest water? Because some of the water molecules act as acid. So half of the ionized water molecules, they act as acid, while the other half of the ionized water molecules, they act as the base. And the consequence of this particular fact is that there is a small concentration of hydronium and hydroxide ions always present. So the water molecules, they are acting as acid, and this water molecule is acting as a base. It will donate H plus ions to H2, and here, sorry, yes, this water molecule is acting as a acid, and this is acting as a base. So it will donate a proton to water, this water, and they will form hydronium and hydroxide ions. I have a beautiful animation to show you how One water molecule is acting as acid. So this water molecule is acting as acid. It will donate H plus to this particular water molecule, which is acting as base. So here this water molecule, by donating the proton, it gets converted into OH minus. So it is acting as acid. And here this water molecule, by accepting H plus ion, it gets converted into H3O plus, that is hydronium. So it is acting as a base. So both of these water molecules, here the red big sphere, it is nothing but the oxygen, and these white spheres, they are nothing but the hydrogen atoms. So one of the hydrogen transferred from one water molecule to other water molecule, and both of them, they are getting converted into here one is getting converted into hydroxide ion and other is getting converted into hydronium ion. The same reaction is shown here. So this water molecule will act as the acid. It will donate a proton to this water molecule, and this water molecule is getting converted into hydroxide ion. It is acting as the acid here. And here this water molecule, which is accepting the proton, it will act as the base and it will get converted into hydronium ion. The reversible reaction is also possible. So this hydronium ion now will act as the acid and it will donate the proton to hydroxide ion. And again, the water molecules will be reformed. So for this water molecule, its conjugate acid is the hydronium ion, and its for this hydronium ion, the conjugate base is this water molecule. And for this water molecule, it is acting as an acid. So its conjugate base is this hydroxide ion. And for this hydroxide ion, which is acting as the base on the right hand side by accepting the proton from hydronium ion, for this the conjugate acid is this water molecule. So this particular reaction is representing the self-ionization of water. So this is the equilibrium between the undissociated water molecules and the ions produced by the dissociation of water molecules. Now let us see the equilibrium constant. So this particular equilibrium is characterized by the equilibrium constant, which can be represented by this. Numerator will contain the multiplication of product of product of concentrations of these ions, and the denominator will consider the product of concentration of water. So concentration of water multiplied by concentration of water is nothing but the square of concentration of water. Yes. So since the concentration of water will remain almost constant, so you can take this square of concentration of water to this side. So we will get this equation. Product of concentration of hydronium ions and hydroxide ions is equal to equilibrium constant for the dissociation of water molecules multiplied by square of concentration of water. So product of these two constants will give you a new constant, which is nothing but the ionic product of water. Now the value of this ionic product of water has been found to be equal to 1.0 into 10 raised to power minus 14 moles per dm cube. So its concept, it's actually unit is mole square dm raised to power minus 6, because this concentration will have the unit moles per dm cube multiplied by moles per dm cube. So the final unit will be mole square dm raised to power minus 6. And this product has been found by conductivity measurements. So using the conductometric technique, the scientists have found out that ionic product of water is equal to this much. Now, at temperature 298 Kelvin. Now this particular ionic product is constant at constant temperature, that is 298 Kelvin. And the concentration of H3O plus and OH minus will also be equal. So replacing OH minus concentration by H3O plus concentration, you will get H3O plus concentration square is equal to 1 into 10 raised to power minus 14 mole square Tm raised to power minus 6. And hence, if you take square root on both the sides, you will find that H3O plus concentration is equal to 1 into 10 raised to power minus 7 mole per dm cube. And as concentration of hydronium ion is equal to the concentration of hydroxide ion, and hence concentration of hydronium ion is equal to concentration of hydroxide ion is equal to 1 into 10 raised to power minus 7 moles per dm cube at 298 Kelvin. So always remember that pure distilled water, it has at 298 Kelvin, that means 25 degrees Celsius temperature, it has hydronium ions and hydroxide ions in equal concentration, that is 1 into 10 raised to power minus 7 moles per dm cube. And the ionic product of water at 298 Kelvin is 1 into 10 raised to power minus 14 mole square Tm raised to power minus 6. Remember its unit is also very important. So students, we will end our lecture. What we have learned today is the concept of dissociation constant, which is a very important concept in ionic equilibrium as well as in physical chemistry study. The concept of dissociation constant of a weak acid, dissociation constant of weak base, and the concept of ionic product of water. So thank you, and keep studying.